good morning to all. Thank you for participating in this research webinar series organized by the Department of Applied Science and Humanities, Physics, School of Engineering, UPS, Dehradun. On behalf of UPS and the organizing team, I welcome you all in this research webinar series. So the objective of this webinar series is to provide a platform where the researchers from various areas come together to present their perspectives on the frontiers of material science research and how the research outcomes may be utilized for solving the problems faced by the humanity today. As you know, we are suffering from coronavirus disease, and there are other issues also. So how material science or how the innovations or research in material science and technology can help solve these kind of problems. So in order to fulfill this objective, speakers from a wide variety of material science research areas have been invited to present their work. Please get benefited from such an august gathering of researchers. In total, there will be 13 talks spread over 5 days. The detailed schedule of the talks has been shared with you. Every day's schedule will be shared with you. And so today there will be two talks which will be lined up. One by Professor D.K. Avasthi, MIT University, Noida, and other by Dr. Foran Singh, Scientist F, Inter University Accelerator Center, Delhi. In order to facilitate an uninterrupted delivery of the content by the speaker, the participants are requested to shut down, disable their microphone and camera during the deliberation. After the lecture is over, question and answer session will start. You may type your questions in the chat box. The moderator, which is me, or one of my colleagues who is organizing this this webinar series, they will ask the question in the same order in which they will be received, and the speaker will thereafter respond to the questions. Now let me introduce Dr. D.K. Avasthi. It is my honor to invite Dr. D.K. Avasthi for delivering this insightful lecture today. So before this talk begins, let me briefly shed light on the illustrious research career of Dr. Avasthi. At present, Dr. Avasthi is the Director General, MIT Center for Accelerator-Based Fundamental and Applied Research, MIT University, Noida. He is also associated to MIT Institute of Nanotechnology as a professor. Before joining MIT, Dr. Avasthi was Scientist H and Head Material Science and Radiation Biology, Inter University Accelerator Center, New Delhi. He is the Associate Editor of Radiation Effects and Defects in Solid Journal and Founder President, Ion Beam Society of India. So we are fortunate enough to have Dr. D.K. Avasthi with us and to listen his talk today. So thank you, Dr. Avasthi, for being with us today. So today, Dr. Avasthi will talk about how the research in nanoscale materials can help in accomplishing basic societal needs related to energy, water remediation, and health. May I request Dr. Avasthi to begin his lecture? Thank you very much.
Okay. Thanks a lot for introducing me, and I am pleased to have this opportunity to give this webinar on a very important topic, advances in material science and technology, organized by University of Petroleum and Energy Studies. So my title of presentation or talk is Advanced Functional Materials for Societal Needs. So this is my plan of presentation or a lecture. I will have a small introduction in which I am presenting nanomaterials as functional materials because they have very special features. So although this is a very popular topic as such and a lot of people are aware, so for the sake of students, I may go a little basic on the special features there, why their special features are there like that. And there are issues like water and environment. These are getting polluted. So then what are the steps or what are the research we are doing in this area, and we are using remediation, that means correction of this water by nano, or detection of the impurities and such things. And energy is also very important in current scenario, because uh, the fossil sources, the conventional sources are depleting fast, and we have to have non-conventional energy sources. So I may touch upon certain things, like there are a lot of areas in this, but I'll touch upon maybe thermal storage, hydrogen storage, thermoelectric, photoelectrochemical spreading of water to get hydrogen, nuclear energy, and so on. The solar cells and those things are quite popular and are being utilized in a big way, but I'm not going to touch upon those things. Then health is also important for the population, for common person, mankind. So which way the nano can help in this, what we are doing in this direction, that I'll uh, brief here. So and then I will summarize. So this is my plan of my talk. I am audible to everyone.
Yes, sir, you are audible. Sir,
Okay.
just a moment. I want to say something to all the participants. Uh,
Yeah.
Stop presenting your screens. All the participants are requested to stop presenting their screens, because some of the participants are not able to view the slides. Slides are already shared, and you have to go to the people link above on your screen. Click on the people link, and then you have to pin Avasthi sir's profile there, and then you will be able to see the presentation. Okay, so you have to click on the people link, which shows how many participants are there, and then you have to pin Avasthi sir's presentation. There are two profiles of Avasthi sir. One is for his video, and other one is for his presentation. So you will have to pin his presentation profile to view his presentation. Thank you. And don't start presenting your screen. Many persons are presenting their screen, that is why the slides are not visible. Thank you very much. Okay, sir, you may start now.
Yeah. So in this scenario of COVID, we are learning new things of uh, meetings and conference, so that we can talk to each other, we can share our ideas. So it's a very good step and by UPS. So I go ahead with the further presentation. So nanotechnology is engineering, basically deals with the engineering of the matter at nanoscale, and one can define these nanoparticles are the matter which is having dimensions from 1 to 100 nanometer, and this has very special properties, and these are listed over here. These are basically size dependent properties. That means the properties of the matter will depend upon what is the size of the grains. Any matter is made of grains, and if the grain size is going in the dimensions from anywhere 1 to 100 nanometer, whether it's 10 nanometer or 70 nanometer or 100 nanometer, the properties are different. So this is a big way, is a big boon to the engineers or scientists to design the materials. And this happens, the other property of this, because it gains special property, is large surface to volume ratio, which means for a given nanomaterial, it has more of the surface area than the volume. And this happens when one goes to in nanodimensional region. And it has similarity with biological system. In biological system, our body is made of trillions of cells, and cells are having dimension of typically say 15 to 20 micrometer, and the very important part of the cell is a nucleus in the center of it, which size may be around a micron, but within the nucleus there is a DNA, and this DNA is basically a twisted pair chain, and whose diameter is around 2 nanometer or so. So that means this, in the biological system, we had very important material, DNA, whose dimension is basically a nano. And that means the nature is having nano-dimensional from ages. We are all having this embedded in our cellular system. And this pair, this twisted pair of the chain of the DNA, it is piled up, but if you stretch it up, then it can be more than actually several feet of the order of meter. But in a coiled stage, everything is packed within it in 1 micron of the cell. Now, you have also semiconducting nanoparticles. And in semiconducting nanoparticles, we know in semiconductors normally, if I have silicon, then its band gap is 1.1 electron volt. Germanium has this band gap of 0.7 electron volt. And no matter wherever you are in the world, these properties remain the same. But this actually do change if you change the grain size of the silicon in the wafer or a film, and if you take the size of the nanoparticle smaller and smaller, then the band gap actually increases. So these are the again some properties which are very interesting and can be exploited for engineering the materials. Physical and chemical properties are also different from bulk. For example, gold has in a bulk state has a melting point of say 1200 degrees centigrade or so, but in nano dimension its melting point goes down to 500, 600 or even lower, depending on how small the size of the nanoparticle is. So, and most important is that why it makes very useful for different, especially in biology, is that it has a high degree of surface functionalization. That means if you have a nanomaterial, a nanoparticle, then you can attach the organic or other functional molecule on the surface very easily. And this becomes a very important tool for many applications. So these are some of the very special properties, very unique features, which are exploited in different ways in different areas of science and technology. So now I come to that actually what is important for human being or the society. Everybody wants to be healthy. Everybody wants to be in a good shape, good health. And for this, very necessary or the requirement is that one should be able to have early detection of diseases. And where nanobiosensors play a very crucial role, and they have to come up in a big way. They are coming in a big way. And so far, actually, if you have any problem, then we run to the pathology lab and then the report comes the next day. But nowadays the concept will come soon. It is on the way that you have a device at home and your problem is detected, and that is conveyed to the doctor by mobile app, and then you get that advice by the doctor then and there. So this is this will be the future, and so where nano is playing a big role and will be playing a big role in biosensors. There is a lot of contamination of food and agriculture products, and this is mainly because there is a heavy use of fertilizers and pesticides in the soil, and this go in the water, and then this go in the water and which you drink, and then there's a problem. And these pesticides and these are also uptaken by the plants and the agriculture products, so they finally go into agriculture products. So it is very necessary to detect this kind of pesticides and contamination by by any device. And here again, nanosensors are coming in a big way, and they will play a big role in this. So next is that we need to have, for health, when we need to have a clean water and environment, and there are nanomaterial based strategies for water remediation. So I will be focusing myself to water remediation using the nano scale materials, and I would also like to share the problems associated with this at industrial level, and how do we tackle this is a challenge to our society, to the researchers. And finally, everybody needs energy, and because as I said earlier, that the conventional energy sources are depleting fast because of depletion of fossil fuels. So one need to have eco-friendly energy sources. Even fossil sources have this problem of pollution also. So we need to have the sources, new renewable sources in which there is no pollution, and you can generate the energy. So first I come nanotechnology for water remediation. I'm going in this order, and so I'll just focus in a couple of slides on water remediation. Okay, so before that, I would like to say that nanomaterials and nanostructures due to large surface area are of interest, which I mentioned earlier, and researchers in area of water remediation, there are a lot of work going on in the lab scale. And the most important part is that whatever we do in the lab scale, often we don't bother about the cost. Whatever we do, and we get beautiful results, very interesting results. And on a test tube, on a beaker, we show remediation of the water and cleaning of the water very effectively. But if this process is not cost effective, then it cannot be scaled up, because cost will come in the picture. Then another problem is that with the nanomaterials, which are in some milligrams, or maybe in some in some hundreds of milligram, or maybe some grams, you are able to show certain things. But when I go to the industry level, then this will be required in several kilograms and much more than that. So that means, again, this nanomaterial which we produce in lab scale, we should have the possibility to scale up and to have the large production possibility. It might happen that whatever we do production or synthesis in a test tube, when we try to do in a bulk, in a large scale, those conditions may not be valid, and you may not be able to make that material in a large scale. So this also has to be looked into, and we have to bother about those things. Next point is that whatever material we used for water remediation, for treating water, we should be able to remove this water after that. Otherwise, we are actually introducing more of the impurities in the water. So these are the three main things which have to be kept in mind in water remediation research. I am sure many of you are maybe interested and maybe doing work in this area. It's a very nice area of work, and very easy to do. So typically the impurities in water are toxic metals like lead, arsenic, chromium, etc. And they come mostly from the industry effluents. And then there are dyes, oils, drugs. Even the drugs are also coming in the water, because whatever drugs people use, finally they get by their urine and by human discharge into the earth, and then it goes to the water. And then there are a lot of lakes and a lot of rivers which are actually seeing these traces of drugs also there, and which is a very serious concern, not only in India but in foreign countries also. So these are some new kind of emerging pollutants coming up, and we have to be that's why it is always said that the drugs are to be taken only with the advice of doctor, and one should minimize especially the antibiotics as far as possible. Now, chromium is one of the major impurities in textile industries. They use certain dyes and certain things where chromium is salt being used, and if this water goes outside, then there is a problem. So here we have shown that a particular nanocomposite, which is consisting of zinc oxide tetrapod and activated carbon based material. So these two things are combined and a nanocomposite is formed. How this activated carbon is made, the steps are here. The sugar cane bagasse is a waste material from the sugarcane industry. So one can actually dry it and grind it, and then you get bagasse powder. Then it is drying. It is done at 700 degrees centigrade for 1 hour. There is carbonization uh, actually occurs, and then you have certain process that you add certain amount of NOH, and there is activation of it, and washing and drying, you get activated carbon. So this is a picture of activated carbon, and this is a picture of sugarcane bias, you can see, and this is the SEM image. And this the other thing is that we have a zinc oxide tetrapod, which are actually produced by uh, uh, is hydrothermal process, uh, then a flame transport process rather. But these two things are actually mixed, and I'm not going into detail how this is made, because this is well established and is a patent, and we have a collaborator from where we get Dr. Mishra now in Denmark, who supplies, who gives this material for a collaboration, and this work is also in collaboration under that. And so this zinc oxide tetrapod, which is shown here, this is a SE image of that. These two things are combined together, mixed together, and put in hydrothermal by hydrothermal method. Is put in a furnace, and we can see that if I use only amorphous this activated carbon, then with the time in 6 hours we are able to remove 40% of chromium. But if I use the tetrapod only, then it removes around, say, 42% or 44% or so. But if I use the nanocomposite, that means the combination of these two, then in 6 hours or so, it removes more than 90%, close to 95%. So it's very efficient, and uh, this precipitates, because and the water from the upside actually can be drained out. So this is the precipitation. So details of this actually you can see in Journal of Chemical Engineering, and this is a student who was involved in this work, and this is a collaboration between MIT University Noida and the Kiel University. So now one more effluent of the oil industry is there is a lot of oil contamination in water from this kind of industries. So here we did some work using zinc oxide tetrapods, which are the same thing which I have shown earlier, and then we have iron oxide nanohybrid. That means nanocomposite of zinc oxide tetrapod and iron oxide. So in this slide, you can see that the zinc oxide tetrapods are made by flame transport method, and this is the shape of the zinc oxide tetrapods. And SEA image you have seen earlier in the previous slide. And for making iron oxide, we take the iron salt and then sodium hydroxide, and this is the process, and we get alpha iron oxide nanorod kind of things. Now these two things are put together, and by hydrothermal method at 120 degrees centigrade, you see that on the tetrapod actually this iron oxide particles get attached. The nanorods actually get attached. The zinc oxide tetrapod is quite big in size. It is several microns, maybe 10 or 20 microns. But this needles of this 4 you can see these 3 or 4 needles coming out. These diameters are about 100 nanometer or so, and on these diameters, actually on these needles, this iron oxide nanorods gets attached. Now what actually, suppose if I do some contact angle measurement, suppose this is the material of this uh, zinc oxide tetrapod and iron nanoxide, iron oxide, and when you put a drop of water, then you can see it is showing a contact angle of 157 degree. So that means it is super hydrophobic. That means ripple water. But anything which is super hydrophobic is basically super oleophilic. That means it wets uh, uh, the oil. That means it loves the oil. So what actually happens that you can see the 4 pictures here. This is a petri dish in which you have water, and the yellow color is because that there is a lot of oil in this mixed with that. And now we put this nanohybrid zinc oxide tetrapod iron oxide nanohybrid. This black color you can see, this is at time t equal to 0, and and t equal to 50 minutes. That means within 50 minutes this yellow color is gone. That means all the oil which was there, since this particular material is loving oil, it has a very strong affinity to attract the oil. All the oil is actually absorbed on this particular nanocomposite or nanohybrid. Now since this is a magnetic also, uh, we put a magnet here, and then all the uh, nanohybrid actually gets attracted and come here with the oil, because oil was absorbed in it. So this is a very good approach, because I mentioned earlier that it is very important to separate out whatever material we introduce. That's the key thing. So here we are able to show, and these are, I forgot to put that this is also published in a very good journal. And we were very enthusiastic about these things, so we tried to uh, contact the industries to implement these things. And by the way, whatever samples we take, we took from industry also, and to do the things at the lab scale only. So in the next slide, I'll show what are the problems which come actually. So practical issues or practical problems at industry level, which we feel, because we are very happy with the results at the lab level, but when we go to the industry, then scenario is different, which I will explain. So in lab level, we do the things at test tube and a beaker, but when we talk to the industry, they say that I want 1 million liter a day. It's a 50 to 100 million liter a day, the treatment of that. So it is written here. Actually, this 50 to 100, it should be million liter, not liter. So the throughput from the industry is 50 to 100 million liter a day, or maybe more. Also depends on the industry. The government has directions to the industries to be zero discharge. The zero discharge means that no wastewater from industry should go out of the industry premises. So most of the industries try to implement this, which have its own problems, and the problem is here. The water treatment plant have several stages of process, which these water treatment plants are very expensive, or few crores, and the final process is reverse osmosis. In reverse osmosis, there is a lot of reject water. You must have seen that in the filters which you use at home. If it is RO based, then you get a lot of reject water. So in the industry also, you get a lot of reject water. So this too cannot be allowed out of the industry premises, and this cannot be stored in a pit. If one stores in a pit, then it should be cemented, because otherwise water will go through the soil inside the earth. That is not permitted. So these are the problems with the industry. But still, there are a lot of industries, I should share, that they do not do this, and this water goes into the river, and that is the main cause of the pollution of the rivers. And you can see this proof very clearly these days, because during COVID, all the industries were closed, nothing was working, and the rivers were total clean now. So this proves very clearly that whatever pollution there is, it is due to the industries. So there is a lot of sewage also which goes to that, but that is not a problem because there are a lot of sewage plants which purify, which actually improves the water, and that water is utilized for the purpose of horticulture only. So these are the problems. Now, these are certain terminology at lab level. When we do the experiments, maximum you will use water for 1 liter or so to show the experiments, and such things are called TRL level 1 to 3. That means you are 3 level means you are able to repeat those things, you are able to do several times, and that is the thing. But if you want to go from some about a liter to 50 to 100 million liter a day, the industry will not take you directly from here to here. They say first show the mid-scale technology. So that's what it is, TRL 4 to 6. And there one has to show the same results for 10,000 liters per water, or maybe more of that. And then lot of technologies fail at that level itself, that they are not able to make that much material, that, and if they are able to make, then they are not able to treat that water at that level. So first it goes to 4 to 6 level, and then it goes to TRL 7 to 9. So from this to this there is a lot of expenses, from this to this again a lot of expenses. So this is the actual picture which I have come across. I visited several industries and tried to share the real problems of that. So there is a mistake here. This is a million liter a day here, not the 100 liter a day. Now, materials for energy, there are a lot of materials, like thermoelectric materials, solar cell materials, hydrogen storage, photo splitting of water to get hydrogen, and this hydrogen can be stored for as energy source. Photocatalytic, if you go to do the photocatalytic processes, then you are actually minimizing the use of electricity. So this is also a useful thing. Supercapacitor, fuel cell, thermal storage, nuclear materials, and so on. There are a lot of non-conventional energy sources. So in this, I will pick up some of that. Nanostructures in thermal storage. So I'm picking up some materials, some areas which are not so common, but they are very useful. And here I will like to show you. Okay, I'll go to directly to that slide. You see this picture here. Consider wax. Wax, you know, moम, जैसे मोमबत्ती होता है उसमें यूज हो रहा है wax. And if you have this wax in a container, you heat it, its temperature will go up. So this heating and temperature going is covered by the basic principle of heat equations, which is ms into delta T. That means mass into specific heat into the change in temperature. So that much heat it's absorbing. That's why there is a temperature rise. But suddenly it becomes horizontal. There is no temperature rise, because at this point it is becoming molten. So here it absorbs a lot of heat. So this heat absorbed becomes basically goes into melting is the latent heat, and this value is quite high. So if you have a molten liquid, then you have a lot of stored heat. So that is the basic principle of thermal storage. And here nanotechnology can help in a big way. And this is the experiment shown over here. This is a small cube. Oh, sorry. This is a small cube, just 2 inch by 2 inch or 2 inch, and there is a wax filled up in it. And one side there's a heater, so it melts. So this is a melt zone, and this is a solid zone. And then if you keep heating, then this melt zone keeps going like this, and you are measuring temperature here, here, here by thermocouples. and it is connected to computer. So this is the facility we have in mechanical engineering department. That's how this curve is plotted. Okay, so now the point is that it takes about 8 to 9 minutes to go to the molten state, but we want that it should it takes if it is pure wax, it is taking about 12 minutes. But when you add some nanomaterial in this, then you have this curve. So that means it has gone to the molten state much earlier. That's what you want. You want to store the heat as a thermal storage as fast as possible. So this is, you can see by the use of nano, we lower down the storage time. I mean, going to the molten stage, so faster it stores. So this is something interesting, and this kind of storage, thermal storage, are used often in the by army. For example, in Siachen, you have a lot of sun, but very cold, -30, -40 degrees centigrade. But sun is very strong. So this there are on the roof you have the slabs which are having this kind of material which becomes molten, and it stores heat. And then the barracks, there is water pipes going through this, which carries the heat and keeps the barracks little warm. So this kind of concept is there in being used in defense. Plasmonics to boost the hydrogen generation by photoelectrochemical process. Hydrogen is a good source of energy because combustion of hydrogen in air with oxygen gives a lot of heat and lot of energy, and this is a good source. And there is no pollution because the byproduct is water. So, and how the plasmonic particles are utilized for that. So first one should understand the plasmonic nanoparticles. So this is a noble metal particle, let us say. So when you shine light, that means, which is basically electromagnetic wave in which electric vector is oscillating like this. So when the electric vector is on this side, the electron cloud relatively moves, and then if it comes this side, it moves the other way. So there is an oscillation of electron this way. And when this frequency of the incident light matches the Plasmon frequency of the metal particles, then there is a huge absorption of the light, and this is what called is surface Plasmon resonance. And this particular frequency actually can be tuned by nature of metal. For example, silver has a Plasmon frequency of 400 nanometer. It will depend on the cluster size, shape, separation, and dielectric of matrix. So for hydrogen generation, by this process, we learn this by nature. And nature is a natural photosynthesis process in which, in the presence of light, the CO2 and H2O in the plant leave. It creates basically energy, glucose kind of thing for the plant, and releases oxygen. So this is something happening in nature. And an analogy is that we use the light energy for photoelectrochemical splitting of water. So that means we use the light in presence of certain materials which are semiconductors, and then this can produce basically hydrogen. So in PC, that means photoelectrochemical process, photons are absorbed by semiconductor and used to split water to produce hydrogen and oxygen. And this semiconductor acts like an artificial leaf, which was here. So here it was producing these two things, but in this PEC, it produces hydrogen and oxygen. And hydrogen is what is wanted, but we have to reach to very high level to be acceptable to the industry. And still a lot of work needed in this direction, and very interesting area of research. So here, it is the work which is in collaboration with Dr. Sahab Das from this Agra Dayalbagh Institute, and they are working in this area. And I had suggested that they should use gold as a surface layer or the bottom layer or a sandwich layer and try this. And this is what they tried, and we have a common student, and we have very encouraging results. So whether we use one just on a top layer of iron oxide, or as a bottom layer, or sandwich in between, or combination of all, there is always a increase in hydrogen production whenever we put a plasmonic layer. We were giving this plasmonic layer as a, which was gold in this case. So now next time what was tried was bismuth vanadate, and iron oxide is also one of the popular material for photoelectrochemical response. We mixed up plasmonic material inside there. That means nanoparticles of gold were mixed inside here and inside here. So in this case also again we had increased production of hydrogen. And this is a schematic shown over here. So one can read more details in this paper over here. And there are possible mechanisms that this is either due to plasmon resonance energy transfer or hot electron holes production, which actually have occurs across the junction, because the semiconductor and metal junction basically makes a Schottky contact, and you have a lot of hot electrons production there, injection of electron at the Schottky, and there could be electronic the optical enhancement due to increase in absorbance. And these are the three processes by which the hydrogen production is increased. Now, it is very important to have hydrogen. It is difficult to store the hydrogen in cylinders. It can be stored, of course, but then they are very heavy to carry and they are not practical. So the best is to use the hydrogen storage material. That means if I have, let us say, palladium, then palladium is something which actually captures one hydrogen, or it can take two hydrogen. So if I have say half a kg of palladium, it can have maybe 100 liters of hydrogen is stored in it, because each palladium atom is having hydrogen. So that is a solid hydrogen kind of thing. So when it goes to gas state, then it is a lot of hydrogen. So this is what actually we tried doing certain things. We utilized GEO, graphene oxide, and this was exposed to hydrogen and 99% of argon. And then we were trying to see a basic study that how hydrogen interact with the graphene oxide. So this is the graphene oxide peak in the beginning, but once we put them together and then we are increasing the pressure of the gas, then this peak shifts. This shift in the peak actually is showing that the interspacing of the geo layers is basically increasing. When it goes to the lower side, that means the interspacing of the graphene oxide layers actually is increasing. So that was showing that actually hydrogen was getting absorbed. So we became very much interested for determination of that how much hydrogen is there. So we did one additional experiment, that is a quantitative analysis of hydrogen in GEO. And this was carried out using a technique which is called elastic recoil deduction analysis. And here in this technique, the ions are bombarded on it, and the hydrogen recoil is detected in a detector. And this is a spectrum. And in the pristine, that means in GEO, this is the curve, the black one. So there is a very little amount of hydrogen at the surface and little inside. But if you have GEO exposed at 1% hydrogen, 10% hydrogen, 100% hydrogen, these are the curves. So you can see that the hydrogen concentration is increasing. The area of the curve actually is the concentration of hydrogen, and this was calculated and which was coming out to be 6.4 atomic weight percent in geofilms. So this was quite high, and these numbers are written here, and the details of this work actually are available in International Journal of Hydrogen Energy. Now, although hydrogen is a potential candidate for energy, but it requires careful handling. As it is inflammable, it can burn in air. So there's a lot of precautions required, and therefore one needs a sensor, a sensitive sensor for hydrogen sensing. And we made one. This is again nano composite, nano alloy kind of thing. These are PD alloy thin films. This is a nano structured film, and this here when we use this film for sensing, the sensitivity was 5% and the response time was 114 seconds. That means it was taking 114 seconds to give the signal that yes, okay, so hydrogen is absorbed. And this change in the resistance of this film is the basically signal for the hydrogen sensing. Now, if this film is irradiated by ions, which was done, and then if it was utilized again, then it is improved in sensing. So it was showing 9% of sensitivity, and response time was 7 seconds only, where it was 100, earlier taking 114 seconds. And this is a picture you can see of the nano alloy film, nanostructured film, the TM picture. And here basically this is the response. That means when you put hydrogen gas in, its resistance increases, and when you remove the oxygen hydrogen, then it goes down. Then you put again, it goes up again. So this process, you can see, this is very sensitive to the hydrogen, and this was actually carried out. This is a work of a student, Deepti, and it was published in Sensor and Actuator. It is actually already published in 2019. Now, plasmonics for photon-induced current. This is also interesting thing. I will show some results. We made some gold zinc oxide nanocomposite film, and this is made by atom beam sputtering setup. Here, a 2-inch atom beam is bombarded on a insulator, which is a matrix here of ZNO, and some metal pieces of gold here. So by sputtering these atoms and molecules of this come here, and by self-assembly process, a nanocomposite film is made. That means gold nanoparticle embedded in ZNO are formed, and this is a picture of the TM picture to show that in some conditions you have zinc oxide nanorod, at the top of which you have a gold nanoparticle sitting. And this is the SPR, surface plasma resonance, visible by the UV visible spectroscopy, which shows that basically is as a plasmonic response. This was showing very interesting photo switchability. That means this particular material, we apply voltage to it, and then when we put light to it, the current increases. When you switch off light, it remains there, and when you switch off light, it comes back. When you put light again, it goes up and remains almost constant. And this can be repeated many times. So that means that this particular material is able to supply electrons in the system in presence of light. So this particular material actually becomes interesting for as a back electrode in solar cells and other devices where you need the supply of electrons in presence of light. Now I'll come quickly to this role of nanostructures in materials for nuclear reactor. In nuclear reactor, there are a lot of structure materials used, and they should remain stable in radiation. And in radiation environment of reactor, where you have fission fragments and a lot of alpha particle, neutrons, and so on. And but the temperature goes as high as 1000 K. The reactor temperature is 1000 K, and so we wanted to study the stability of these materials as a function of grain size, going in the nano size. So we had two projects in this direction. One for making the setup for 1000 K, which was set up at IUAC, and one more project we had on grain size dependence, which with IIT Delhi and BRC. IIT Delhi is the main PI there. We are collaborator. So this is the setup implemented by Dr. Pavan Pularia at IUAC. This is a project I took in 2010 or 11. And so one setup for making irradiation at reactor-like condition. That means temperature should be 1000 degrees centigrade or so. And then at that temperature, you irradiate that material. So this is a heating stage, and this is a part to do the beam, and this is the actual setup, and this is a flange through which you can see inside. When it is heated, it is red hot, and in this condition the ion beam is bombarded here like this. This is schematic. And now then we study that material under the reactor-like conditions. That means the radiation which comes, which is there in the reactor, but we are simulating by ion beam from accelerator, and this is at high temperature as here, and we study how stable is that material. So these are the studies on the stability of those materials. So I don't go into those details because time is a limiting factor, and I skip this. Now I quickly come to nano in diagnostics and therapeutics. So in health, both are important, diagnosis and therapy, and nano is playing role in both the ways. I explained the DNA in the beginning, so this looks like here, this is a DNA chain, and this is GC and TA, and these are the sugar and phosphate at the backbone. And I think I have limited time, so I should skip this. So there is a lot of application of nanoparticles in onset cell, and this could be utilized for diagnostics as well as therapy. So in diagnostics, there are a lot of biosensors. This nanoparticles can help in bioimaging also. So sensitivity, if it is improved, then you can have early detection. And then therapy treatments, that means treatment using the gold or nanoparticles or other nanoparticles. So the gold nanoparticles are being used for drug delivery, or magnetic nanoparticles are also being used for drug delivery. So these are the things which are on a research scale, on the lab scale, not employed in the hospital so far. Then magnetic nanoparticles also can be utilized for hyperthermia. That means you take these nanoparticles by magnet, you inject them, and by magnet take to the cancer cell, and then you magnetize and demagnetize from outside, which creates a hysteresis loop. And hysteresis loop is nothing but heating of the magnetic nanoparticle, which are in touch with the cancer cell, and they kill the cancer cell by heating. So it is well known that cancer cells get killed at, says, typically 45 degrees centigrade or so. So there are already nano-based drugs in the market, but they are very expensive. So there is a lot of research required in this area to minimize the cost. So I think I should skip this. Zinc oxide tetrapost based sensors have been utilized for Helicobacter pylori. This is a particular bacteria found in colon, in intestine, and is responsible for colon cancer. And the strategy, therefore, is to detect the Helicobacter pylori in the blood using nanobiosensor. And this is what we have actually shown in this particular paper, this ACL applied materials and interfaces. And here we have shown that actually the ion irradiation improves its sensitivity. So this is a device which is just a finger kind of thing. This is something like that glucose testing chips you have the same size. And here, this area, we put the zinc oxide tetrapods, and then some irradiation is done, and then we attach certain immobilize the antigens here, and then we put this with uh, uh, the blood serum, and then it gives the signal for that something is there. And we have tested this for uh, selectivity also, that it is selective for pyroli bacteria, Helicobacter pyroli bacteria. I think there is less time for this also, but I'll quickly say that there has been research in our MET where we utilize this was not done by me, this is done by Jagriti Nara. She is right now in, she was earlier in nanotechnology, now in Jamia Hamdard. Silver core shell palladium, and this was utilized for detecting this particular alprazolam. And alprazolam is an antidepressive drug, and high use of this actually can cause death. And this is what the cause of the death of Sunanda Pushkar, which was very famous in. This was a big news a few years back, and normally this test takes about a day. Next day, pathological lab gives the results. But what is shown here, that this small device, if you put the blood here, then blood serum, then it can give the result then and there. So this could be used for clinicians as well as for forensic toxicologists. In forensic sciences also it will be utilized. They have a patent on this. In the same way, we have utilized GO, graphene oxide gold nanocomposite, for detection of acetylcholine, and this is a enzyme released in brain for. There are a lot of brain-related problems in old age, and this is related with the certain enzymes, and one of them is acetylcholine. And this work is in cooperation with GMU, IAC, IUC, and MIT University. So, Dr. Pandey, can I take some time more, because it's 11 o'clock?
Yes, sir. This is Santosh.
Yes, sir. You may.
Okay. So I take up some very interesting thing. This is the ion beam therapy, and although ion beam therapy has nothing to do with the nano, but then this therapy can improve further by the use of gold nanoparticles. So I will show some results, lab level results related to that. So first, let me explain that ion beam therapy. And this is a curve which is a standard curve, well known in literature. And here on the y-axis, you have the relative dose of the radiation. And here, this is depth in water. That means actually human body, 80%, 75 to 80% is water-like thing. So the simulations are done with water. And you can see normally X-rays are used or photons are used. So I see that cobalt 60, you are familiar. If the cobalt 60 is exposed, then this is the curve for radiation of cobalt 60. That means as you go down inside, the dose actually is decreasing. Okay, like this. So it is having more dose near the surface and less inside. But suppose cancer is here at in the body at 12 centimeter. Okay, so the dose at the 12 centimeter is this much, very small. Whereas before that, the dose was high, so which was not desirable. That means it was actually killing normal cells more, and affecting less to the cancer cells at this point, because this dose is responsible for killing the cancer cell. So if you have an ion beam, then the, the, the dose deposition curve is something like this. And this is governed by something well known in ion beam. Those who are familiar with ion beam, this is called drag P, which is very sharp. So if the cancer is at 12 centimeter, then you can see huge energy deposition, much more, much more, many times more than the cobalt 60, and therefore it kills more effectively. And the even more interesting thing is that there is no effect beyond this 12 centimeter, very small effect. And in this region also, at the entry site also, this is much smaller than this part of the photons from the cobalt 60. So this is the basic principle, and it's been utilized for ion beam therapy. And all leading countries, rich countries, have this therapy. Is very expensive in Germany, Japan, France, USA, and now this is being set up in Chennai, Apollo, and it will be coming later in Bombay and Delhi also. So with this reference, I wanted to show some experiment on interaction of first of all glucose capped gold nanoparticle with HeLa cancer cell. This is a particular type of cancer cell. This is the cancer cell which you see here. Okay, and this is the gold nanoparticles. Black dot are the gold nanoparticles, and this is a survival function. That means different concentration of gold nanoparticles are put with this cells in a culture, and then we see that cells are still surviving. One means 100% survival. So this is a survival fraction. So no matter how much concentration of this, they are surviving 100%. That means gold as such are not actually causing death to the cells. So that means they are not toxic at all. Now, this is a picture again. In this picture, it is difficult to say that whether these gold nanoparticles are inside the cell or on the top of the cell. So we did a cross section of that. So we cut that cell. This is called microtomy, and then a cross section of that it is seen, and you can see these black dots, which means that these are the gold nanoparticles. This shows that gold nanoparticles has gone inside the cells. Now this is the real experiment here. We have proved that gold particles have gone inside the cancer cell. Now this experiment, these are the two curves, 1 and 2. One is the normal cancer cells. Normal means that without particles, and this curve is with the particles. So this curve is lowered down, and here you have a dose and the survival fraction. At 0 dose, both of them 100% surviving, fine. At here it is 0.1% survival, means 10% are killed. 10% are surviving, 90% are killed. So I go on this side, you can see that for this cells, the cells without particle, I require around more than 3 gray dose to kill 90% of them. But here you can see I need only around 2 gray only to kill 90% of the cells, cancer cells. So that means I am able to reduce the radiation therapy dose for if the gold nanoparticles are inside the cancer cell, which is very interesting and very desirable. So this is what I wanted to share in this direction. Okay, with this I would like to say that we are having currently we are having I must acknowledge that we are having DST FISC project, DST low energy etc. being set up at ACSM with Professor Ajay Gupta. He'll be giving a talk sometime later. And we have some project from BNRS for plasma engineered metallic superhydrophobic surfaces for harvesting water from moist air. This is in mechanical engineering department. And then we have one project from UGC CSRD Kalpakam on SERS, Surface and Raman scattering. I skipped that slide because of the lack of time. In our group, we have also WAS-A project, means Human Scientist A project of DST on metal-rich metal oxide for our RAM. So this is also a nano-dimensional region. And we must acknowledge that we do experiment at IOC Delhi, RRCAT, IOC Indore, IGCAR, Kalpakkam, Proton Factory, Japan, Daisy, Germany, and Alatra, Italy. This is a summary that we discussed what nanotechnology is and how it is being utilized in water remediation, the challenges therein, and then materials for energy, and the nanobiosensors. I must also say that I mentioned the collaborators and contributors. A lot of people from MET, Monica, Mahima, Nidhi, Utkarsh, Subhasha, Kanika, Jagriti, Lakshmi, Chetna, Chetali, colleagues from IUAC, Mishra, Rainer, and so on, Dr. Tyagi, Sikavar, Anuradhas, Abdas. And we look forward always for national and international collaboration in area of plasmonics, energy materials, nanobiosensors, simulations, and I thank you all.
So let us thank the speaker, Professor D.K. Avasthi, and we'll have some questions from the participants. One question is from Shija Mol. She's asking like in situ studies, can in situ studies be done for biomaterials? Is it possible?
In situ studies of biomaterials.
Yes.
What kind of in situ measurement she wants to do?
She did
It
not
will
mention
depend
it.
on that. Actually,
Okay.
it depends on the. Suppose I'm studying some in situ biomaterial. I'm studying. Suppose I'm studying as, let us say, toxicity. Okay, so
Yeah.
my parameter is that how I'm seeing the toxicity. Okay, so
Okay.
I should be able to measure those things at shorter interval of times. Then only I will be able to do in situ. For example, I take a different example. Suppose I say that I have some electrical characteristic which is changing with time. So if I'm looking at electrical signal at different time, I am doing in situ measurement. So
Okay.
that's the response to her.
Yeah. Another question is from Biswajit. He's asking, you choose gold than silver, and the plasmonic effect of gold is lower than silver. Still, you chose gold than silver. Why?
It's a very good question and very important because for biological application we did not choose silver because silver is known to be toxic, and that's why we took gold nanoparticles. And gold is also utilized in Aruda in a big way in Swan Basin. So we are more comfortable with gold for this biological applications. In other applications, like thermal storage, we utilized basically zinc oxide, which was not gold, and so the choice is there. So silver could be utilized for surface enhanced thermal scattering and other applications. Sure, I agree
Okay.
with you.
Uh, yeah. One question is from Pranjali BHU. She's asking what stoichiometry or ratio was used for gold zinc oxide.
Okay. Actually, you shouldn't say that it's stoichiometry because this is not a zinc oxide and gold compound. It is a zinc oxide is decorated with gold nanoparticles. So one can talk in terms of gold content in zinc oxide.
Okay.
So this was we had actually done the experiment from say 5% to 30%.
Okay.
So different results are given in that particular paper. So the gold content was varying from 5% to 30%.
Okay, sir. And there's a question from Rajabu Nisha. She's asking which magnetic material is used to treat cancer and will it have any side effects?
Yeah, there's normally iron oxide nanoparticles, very small size, are people are trying, and they have shown that they are able to produce the heat, but they are still to be used uh, with the human body. First, the experiments are probably already going on the mouse model. That means first the experiments have to be proved on rats, and then when they are proven to be effective, then the human trials can start actually.
Okay, sir. Some more questions are there. Let me ask them. Some questions were from simulations. Let
Yeah.
me. Okay. So the question is, can we perform the analysis by computational means?
Uh,
The
yes,
question
sure.
from yeah.
Actually, the whatever I have shown here, their simulation can come in the picture when we are actually optimizing a material for a particular application. For example,
Okay.
suppose I want to dope say semiconductor to get some behavior which is useful, some defective states in the visible region, which is useful
Mhm.
for photo splitting of water or photocatalytic application. Okay, so then
Yeah.
there could be density functional theory or such kind of things. They can optimize and tell that which which doping is better and how much percentage of this is better. So this can
Uh-huh.
minimize the experimental efforts. So normally
Okay.
in big groups in foreign countries they do
नहीं क्या
like
था
this.
लाइव
They take the
इसका
Yeah.
input
Yeah.
वीडियो
of
तो
the
रिकॉर्ड हो ही रहा है
simulations.
Yeah. One
हेलो
question is
आवाज आ
from
रही है
Raj Kumar. He's from IIT
हेलो
BHU. He's asking, what is the role of
हाँ आवाज आ
metamaterial
रही है
for
आपको
solar energy harvesting?
हेलो
Uh, I have not touched upon in the metamaterials, and metamaterials is a very interesting area,
Yeah.
and in different areas they are, but not in the solar area. Probably it could be utilized in the way because metamaterials can have a good
मैं ये कह
absorption
रहा था
in
कि
higher region
इसमें
also,
वीडियो तो रिकॉर्ड हो ही रहा है
Mhm.
because although
मैं कह
maximum
रहा
of
था
the heat
वीडियो तो
is
रिकॉर्ड हो
confined
रहा है
in
यहाँ
the
पे
visible region, but the higher
ओके
region
और उसका
also
मैंने
cause
फोटो
lot
तो
of
खींच
heat,
लिया है
and the
रिकॉर्डिंग का
metamaterials could be utilized in a big
स्क्रीन
way.
शेयर नहीं हो
And
पाएगा शो नहीं
metamaterials
हो
have
पाएगी
other
स्क्रीन
tremendous
एक्टिव नहीं हो
applications in
पाएगा
biological
ठीक है
systems.
हाँ बाकी तो हो
Yeah.
जाएगा
Okay, one question is from Dr. Prashant Rawat.
नाले
He's
एक तो
faculty at
सबसे ऊपर तो
UPS.
स्टूडेंट है
He's asking like how well do the simulation of ion
चलिए
beam
फिर करते हैं
bombardment of
हम
materials under high temperature compared with the actual weathering of reactor walls under nuclear radiation, principally neutron bombardment.
Okay, yeah.
Yeah,
So this is a when I say simulation, this is a in our case it is experimental simulation, which means that in the reactor there is a wall and there is a lot of radiation and heat. Okay,
yeah,
so now I take this material and I want to test different materials. So this experiment in reactor it cannot be done. So what is done is that material is taken in a chamber where the ion beam comes, which represents the radiation equivalent to neutron or fission fragment or what. One can choose the ion accordingly, and then
yeah.
temperature can be raised, and then we can test that material. So it's a simulation, but it's the experimental simulation.
Okay, it's not like you develop equations and so on, and then
No,
you
no,
simulate,
no.
you write
But then
algorithm.
no, but
Yeah.
then to explain those results, we further do simulations taking the theoretical models, which are there in our papers.
Okay, so you mean like whatever conditions are there inside the reactor that you mimic outside by taking out those
Correct,
components,
correct, correct.
you
Is a
mimic
mimicking.
outside.
Yeah,
Yeah, you
correct.
don't do that in the computers. Like you consider that material, for example, if it is nickel, chromium, or any other invar kind of alloy, and
Yeah,
then you write various to understand the various physical mechanisms. You write equations and then you
right, right,
simulate
right.
it. You
Yeah,
don't do like that. Yeah, you
but
do. Yeah, yeah,
nevertheless,
yeah,
yeah.
yeah.
But nevertheless, there are the groups who does the direct simulation also. But we
Yeah,
are not doing that. We are not doing that.
yeah. I do that basically. My
Okay,
area is that only. Yeah,
okay,
I develop mathematical models in phase field method using phase field method, and then I
okay,
irradiate the material. The way it is done in nuclear reactors, and then we see
okay,
how the concentration of various species evolve,
okay.
and we
Great,
see
great. So maybe
precipitation formation of
we can discuss
yeah
sometime. We can talk about
yeah.
this. Yeah, sure,
Yeah, we
sure.
understand formation of voids, the radiation-induced segregation, and all those
Yeah,
things, formation
right,
of
right.
patterns, and so on. Yeah.
Yeah.
Yeah. One more question is from Novin Senetra Roy and he's asking, how do you manage to print it on a normal paper for sensing? I don't understand this.
There are techniques
How
for
do you
that.
manage? Yeah.
There are descriptions given in the paper, which is not very difficult, and
Okay.
there are solutions come. There are different kind of inks they come. I will not know the
Yeah.
technical detail of those right now, but they are there in the papers.
Yeah.
Yeah,
Okay. One
and
question is
choosing,
from.
uh, yeah,
Yes, sir. Yes, sir. Go ahead, please, please.
and choosing particular paper is also important because we try different kind of papers and then we select some of them. So there is a lot of
Mm,
research in this area also.
yeah. Sir, one more question is from my colleague, Dr. Prasad Rawat. He is curious to know if in ion therapy, the idea would be to use different types of ions for attaching malignant cells lying at different depths.
Can you repeat the question once again, please?
I mean, he's saying the importance of using different types of ions for attaching malignant cells lying at different depths.
Okay. First of all, I would like to correct that there is no attaching of the ion. This is the ion bombardment. This is the
No, no,
energetic.
attaching malignant cells. Using different types of ions for attaching malignant cells lying at different depths. I mean,
No,
he
no,
mean
no.
to
We
say,
change.
yeah,
We change the energy. We are talking
yeah,
of
yeah,
ion
yeah,
beam
I
therapy,
understand.
right? We change the energy.
Yeah,
I
yeah,
can
yeah,
show that. I'll just show that. Okay, just a minute.
yeah.
So here, suppose cancer cell is 12 centimeter, then energy was 250 MeV per nucleon. But when suppose it is at 18 centimeter or so, 17 centimeter, then energy is 300 MeV per nucleon. So
Yeah.
then energy deposition is high at 17 centimeter. So we are changing the energy, not the ion.
Okay, okay, yeah.
Okay.
So one question is from Debanjan Sen. He's asking, like, is it possible to perform molecular simulations analysis in order to understand the diffusion of nanoparticle protein membrane system?
Uh, this is possible, but I have no expertise on this area. People do molecular dynamic simulations,
Yeah.
but I have no expertise in this area.
Yeah, it can be done. I can answer that.
Yeah,
Basically, molecular simulations can be done to understand the
correct.
diffusion behavior. But molecular dynamics, the time scale again is very small. So you do
Yeah,
KMC or for KMC and field theoretic modeling.
yeah,
For because diffusion has a long time scale. Unless things happen at a really great amount of time, it's difficult to understand what is happening inside the material. So again, you can get some signatures of the phenomena you are studying using molecular simulations. But to know more about it, you need to use either kinetic Monte Carlo or even field theoretic modeling, like phase field or something else. So one more question is about hydrogen gas sensor. So Rohit Pawar is asking, for hydrogen gas sensor, you measure change in resistance or conductance. And yeah, I mean, what do
actually,
you do?
yeah, we are measuring basically current, and current change is whether you see resistance or conductance. Is just question of how you are
Yeah,
saying
yeah,
that.
yeah,
Okay.
yeah.
Yeah.
Yes, yes, yes. So one question is from Ravi Kumar. He's asking what technique is used to identify the structure of nanoparticles. This is simple. Yeah.
Structure of the nanoparticle
Yeah, one
can be,
technique.
by TEM, SEM, and the phase of that by X-ray diffraction. Size also one can get some idea from Scherer formula from X-ray diffraction. So this kind of thing we do.
Okay. I think we don't have any more questions. So let us thank Dr. Avasthi for giving a very insightful, very nice lecture, which is which is very understandable. It was not having a lot of mathematics or too much technical things in it. So we are really grateful to you, sir, for coming, for giving your time and giving such a nice lecture. Thank you
Thank you.
again,
Thank you.
Dr. Avasthi. Thank you very much,
Thank
sir.
Okay, welcome. Thank you. Thank you.
Okay. Participants will again meet at 3 p.m. The talk will be by Dr. Foran Singh. and this will be on phase transformations in oxide. So till that time, take rest and enjoy the day. Thank you.